Hello, today we're going to look at vectors and dot product. The dot product is vector multiplication. The answer is going to be a scalar. That's going to be just a number. So if you look up at the formula up here for dot product, u dot v is going to be u1 v1 plus u2 v2. So how this is going to work, let's look at example 1 and we'll try this one together. It's very simple. So if we take the dot product of these two vectors in component form, then our answer is going to be 5 times 3. This would be u1, u2, v1, v2. So we have vector u and vector v. The solution is going to be 5 times 3 plus -2 times 4. So the dot product is going to be 15 subtract 8, which equals 7. Example 2, properties of dot product. The properties of dot product are the same as number 1, commutative property, u dot v equals v dot u. Number 2, you can see u dot u is equal to the magnitude of u squared. Number 3, 0 dot u equals 0, zero product property. Number 4 is the distributive property. And number 5 is the associative property. Looking at example 2, we're going to start with w dot w. So if you look at what vector w is, it's 5, -2. So we're going to do 5, -2 dot 5, -2. So according to dot property, this is going to give you 5 times 5 plus -2 times -2, and that's going to equal 29. Okay, the magnitude of w squared. So we're going to show, we're looking at number 2, and we're showing that the left side, w dot w, is equivalent to the magnitude of w squared. So let's look at what the magnitude of w squared is equal to. It should give us 29 again, correct? So we take the same vector, and this time we're going to find the magnitude of it. So to find the magnitude of vector w, you're going to do the square root of 5 squared plus -2 squared. And that's going to give us the magnitude. So that's going to be the square root of 29. And now we want to take the magnitude and we want to square it. So we're going to take that value and square it, and it's going to give us 29. Therefore, A equals B in those two examples, proving number 2. All right, the next one we're going to do is look at C and D. C and D is going to show us how number 4 is equivalent. So looking at C, we have V plus W. So when you're adding vectors, you would start with vector V, which is 1, 0, and you're going to add that to vector W, which is 5, -2. So that's going to give us a vector, and we're going to add the horizontal components together, which is 1 plus 5, so that equals 6. And then we're going to add the vertical components together, 0 plus -2, and that's going to give us -2. Now what we're going to do is we're going to take that and do the dot product of vector u. And vector u happens to be -3, 6. So calculate the dot product of that. It's going to be 6 times -3 plus -2 times, let's see, 6 times -3 plus -2 times 6. So that's -18 minus 12. -18 subtract 12. and that's going to give me negative 30. So on number 4, we just did this side. Now we're going to prove that it's equivalent to u dot v plus u dot w. So looking at our problem, it would be v dot u plus w dot u. So looking at that, let's take v dot u first. So v dot u is, vector v is 1, 0, dot, and vector u is negative 3, 6. So when I take the dot product of that, I'm going to get 1 times negative 3, which is negative 3, and 0 times 6, which is 0, and that's going to give me negative 3. I'm going to take that negative 3 and I'm going to add it to the dot product of w dot u. So w is 5, negative 2, dot u, which is negative 3, 6. So let's take the dot product of that. That's going to, now we'll take the dot product of w dot u. So that's going to give us 5 times negative 3, which is negative 15, plus negative 2 times 6, which is negative 12. And negative 15 and negative 12 is negative 27. We're going to add those two dot products together. So negative 3 plus negative 27 equals negative 30. So you can see that the left side on number 4 was equal to the right side.